Yeah, so actually, as Christoph said, this might be the thing for you if you're looking at efficiency or you're looking at your I/O path. And Keith mentioned that libNVMe wasn't for like bypassing the kernel. This might be a bit of that nasty bypass as well. But at least this will be a talk about some of the things you can do when you're programming sort of emerging storage interfaces with a focus on making it easier for the user when you're seeking efficiency and actually making it easier to get control on the commands that you're sending to your device. And so why this sort of focus on things? Well, with the lovely NVMe, we got some new media that was really fast. We got a nice queue-based command response protocol. And in that protocol, you have your opcodes, and you can send whatever you want to your device. That is, if there's infrastructure that allows you to construct a command and send it down there. So with NVMe, we basically have new devices doing old things a lot faster. So that requires efficiency from the software side. And I'll be talking a bit about how do you get that. And there's also new devices doing old things in new ways. So basically, there are the traditional block storage where you have your reads and writes, but you also need to do a bit extra since those low-level responsibilities are being pushed from the device up into the host, and the host now needs to manage some more stuff, so you need some control or some flexibility in how you construct commands that aren't just reads and writes. And sort of to push to leverage these new sort of devices, well, the further up the stack you can push that stuff, perhaps even all the way into the application, well, there you can actually take even more advantage of what those new devices provide for you. And there are new devices doing completely new things we don't know about yet. We have like these computational storage things, and who knows how they're gonna use or exploit, or what you might call it, the NVMe standard and the infrastructure available to send send commands to your device. Yeah, so basically this is about what are the software infrastructure available to sort of provide efficiency and control with the sort of the perspective from the application developer. What's available and how can you use it? So I think the latest and greatest is the IOU Ring interface, which is a really neat user space and kernel communication channel that you can use as a transport mechanism for your commands. So the U-Ring is sort of similar in design to the NVMe. It's queue-based. You have your submission queue that's populated by user space, consumed by the kernel, with these fancy SQEs here, where you have your opcode, a bunch of flags, and you have your completion queue that's populated by the kernel and consumed by user space. And where the NVMe command has your command identifier on the set up on the SQE, and you can match that up on the CQE. Well, with IOU Ring, you have the nice user data parameter where you can pass anything on your submission, and you'll get that back again. That's a really neat feature when you're using the interface. And for using them, IOU Ring has a system call for setting up or for doing your submission and completion of these commands. And there's a system call for setting up your rings or your queues. And there's some resource registration for setting up shared resources. So why would you be interested in this in IOU Ring? Well, that would be to get more efficient execution. So I took these numbers from Jens's paper article where he describes IOU Ring, and he said like the previous interface was at around 600K IOPS in an interrupt-driven mode. By using IOU Ring, you can double that when you're interrupt-driven, getting 1.2 million IOPS. And when you start to enable stuff like polling, well, then you can reach 1.7 million IOPS. And adding to that is very flexible. It works with the Unix file abstraction, not just when it's a block device. Sort of fits in very nicely with the entire encapsulation of the operating system. And it has sort of this growing command set of opcodes, stuff that you can get the kernel to do when you do post an SQE. And it's adaptable. You can add a new opcode and add handling of that stuff inside of the kernel. And when I familiarized myself with IOU Ring, I wanted to see like what happens. Why do I need all of these fancy features? Why do I need to register files and fix buffers? I thought like, do I really need to do that? And what happens when I enable these things? So I tried to sort of reproduce the numbers that Jens did on an old machine I had lying around. And I sort of got, slightly different results, but of course there's a different CPU, a different machine, so you will get different results. But what I saw was also that it is definitely, when you look at latencies, those are lowered, especially when you sort of enable these features, which is why you want to do it, the context switch from user to kernel space. Well, you can lower that by doing the file registration and the buffer registration that takes some of that response overhead when you do your commands. And you can then get sort of, increased throughput. So in the interrupt-driven mode, I got around 1 million IOPS. And when enabling, the submission queue polling by the kernel, I actually hit what I thought was a whooping 2 million IOPS. So it seems like this is a really nice interface to use. It's flexible. You can do a lot of stuff with it, and it marks a bunch of spots when it comes to getting efficient use of the I/O infrastructure. And the only challenge is sort of that there's a lot of stuff that you need to learn about. There are restrictions once you start enabling some of these features. So when you enable the fixed buffer stuff, that doesn't apply to all opcodes. I saw a weird thing that when you enabled the I/O polling as well as the submission queue thread polling, actually degraded performance. You gotta know stuff like that register files is required for SQT. You have to change how you do your commands once you enable some of these things. So I would say it's not the easiest thing to use. However, there's a bunch of man pages that document it really well. You have PDFs, mailing lists, you have GitHub, and talks all over describing how to use it and how to use it efficiently. And for the ease of use, then if there's a library, the libaio ring, and if it doesn't make it easy, at least it makes it easier, taking some of these low-level concerns and wraps them in a library. However, there are still stuff that you have to read the main pages to make use of when using the library and IOU Ring directly. So what else do we have when programming stuff? Well, also as Keith mentioned, there's all of the iOctls, and the interface itself isn't really efficient, and it's not very flexible. When you add stuff, you are bound to that 32-bit NVMe command for the rest of your life, and you have to double stuff then for the 64-bit responses. And however, the NVMe driver iOctls are very flexible, and even though you maybe shouldn't do it, you can use them for I/O. However, they won't be super efficient, but well, it's available and you can do it. And you can basically change without changing the kernel, whereas with IOU Ring, you add an opcode, add support for in the kernel. Here you can actually pass that command directly from user space, create your submission queue entry, and throw down almost any kind of command. The kernel does do some nice things to preserve the sanity of the subsystem and the driver and all of that stuff, but there's a lot of flexibility there. And then, of course, you have the good old SysFS, where you can get your driver attributes and all of that stuff. So Linux basically have pretty much what you need. You have the IOU Ring for efficiency. You have SysFS for your convenient device and driver information. And for everything that doesn't map into, you have the iOctls to do those other things. So why would there even be anybody considering stuff like SPDK? Well, that's a good question, right? So they sort of, as advertised, you could get 10 million IOPS from one thread. Of course, this is it's not something you can compare directly to the number of the 2 million IOPS with using IOU Ring, since this is using a completely different CPU. I think it's important to say that. And I actually really wanted to reproduce their numbers, but I didn't have that $12,000 CPU lying around, or the 16 NVMe drives they used to reach that spot. But still, I wanted to explore, like, what do you get when you sort of go the SPDK way? Because it seems like it is very efficient and is also very flexible. Without changing anything but user space code, you can have any command sent down to your drive. So as an application developer, that is sort of nice. So I did like a quick view on taking a regular physical drive, NVMe drive, and it did 4K random read at Q.1. And SPDK did quite well. So IOU Ring with the submission queue thread polling and register files enabled, I got these 117K IOPS. And doing the same thing with SPDK, I got 150. So that was sort of saying, okay, so that might be why people would go down that route. But of course, this means that you separate yourself from the entire ecosystem that is provided by having an operating system, sharing your resources, protecting you from doing things and from hurting yourself and others when you submit I/O. However, the advantage is it might just be that performance might be slightly better, and you get to run on the Beastie OS as well, if that's something you want to do. So it seems like out there now you have some pretty good options when you want to get efficient interfaces, but it's not really great that you have to change all of your code and know all of these low-level things when you have your I/O path. So with this project that we're working on, we really wanted to change that and see, could we get sort of a unified API, primarily for NVMe devices, where we could encapsulate all of those low-level details on your fast path to sort of say you could produce a cross-platform transport mechanism for NVMe commands. Or you could say instead of a user space kernel communication channel, is a user space to device communication channel using whatever is available. So this is standing on the shoulder of giants. It's using IOU Ring underneath. It's using SPDK if that's what you want. But it tries to sort of encapsulate that so that you can worry about creating your commands, sending them down, not be worried about how it's actually being transported. So we really wanted to focus on being easy to use. We want to reap the benefits of the lower layers, but without sacrificing efficiency. So we really wanted this mantra, high performance and high productivity, in the sense that we should be able to tap into the performance provided by these efficient interfaces, and it should be easy to use. You shouldn't be concerned about the lower levels. And adding to that, provide a bunch of tools and utilities, including tools to build other tools. So once you start doing stuff like this, you typically need some small test program. It should be easy to produce a new one of those. So looking a bit at what the API itself looks like. So at the base level, there's this lowest level interface, which is sort of an encapsulation of getting device handles, enumerating device, probing devices for their geometry, and managing memory in terms of producing buffers to send down to your device, and then the command interface. So let me jump into what this stuff looks like. So here is using a command line utility that uses xNVMe, where you see two devices on the system. One here you see the output is, you can see here it's producing this funky looking identifier with a PCIe ID and a namespace ID here on the back. And that's because this identifier here says that the drive is attached to the SPDK driver. And this other one is another device that's attached to the Linux kernel. So as the developer, you don't really have to care about it. You can see your devices, whether they're working with one stack or the other. And then you can, there's a bunch of parameters that's really essential when writing storage applications, such as your sector size, what's your maximum data transfer. All of these sorts of parameters are pushed into something that we call the geometry. And here you see a conventional geometry. For other type of devices, you might see that they have these parallel units, or they might have zones, and they'll put them in there. But on a regular NVMe drive, those things will just be 111, and you see the number of sectors and the sector size and that stuff. So using the actual API looks like this. So in your application, you just do xNVMe device open, and you provide that identifier. So if you've used SPDK before, you have like those 300 lines of enumeration and all of that stuff, and here you just provide it, and then it opens up if it works, or gives you a fitting error code if it doesn't work. And it's the same code whether it's using your the operating system, or whether it's using or bypassing the operating system. And in order to get to sort of make it easier to have to make use of stuff like DMA transferable memory, then there are two sets of allocators. And one is called the buff allocator, just regular buff that has virtual to physical lookup, which you can deallocate. And these function calls typically just dive down into the SPDK memory allocators. If you use the different backend, well, then they'll just use the regular virtual memory allocators. And if you explicitly just want this to allocate regular virtual memory, well, then you use the buff vert alloc and buff vert free, and they will typically just map into libc. You could also retarget them for stuff like tc malloc. And then the command interface. The command interface is, you have the pass-through style, where you tell it, give it your device handle, and provides your submission queue entry, your buffers, and your metadata buffers, and some options, and this request object, and you just send the command down. So that's one way of doing it. The other one is using the command encapsulation. If you don't want to create the SQE, the library will do it for you. For opcodes that are defined in a spec, well, then you can expect that the library will have a helper method that'll do the setup for you. And you can then either execute your commands in a synchronous fashion, and by that I mean that when you do, for instance, a read here, you provide the argument of a synchronous command, and what you do then is check the error code, which will tell you how well or not it actually managed to submit this command, and then you check this request, the request object for the completion status. So once this function returns, it would at least have tried to submit your command, and if it was submitted, it will have the completion ready for you. If you go the other way of being asynchronous, well, then you can only check your submission status, and you will have to use some other infrastructure that I'll show now on how you would work with the asynchronous fashion. And that stuff is encapsulated in a context, and those contexts then maps down to either an IOU ring or to an SPDK IOQ pair, or some other thing if you are implementing another backend to send commands down to your drive. And you can terminate these or construct them. You get some helper methods to get the depth of those queues, and you can probe them to ask how much I/O is outstanding, currently outstanding on your queue. And then for your completion path, that's callback based. So on your commands, you provide a callback function, and then you reap your completions either in a blocking way using wait, which blocks until your queue is empty, or you can have something that returns immediately that just pokes and see if there's anything in the queue and returns how much was completed while invoking this function call. And these things are then wrapped inside of a request object where you have your completion, you have those asynchronous fields for your queue or your context, your callback, the callback arguments. There's some space reserved here for backend specific data, which the backend can fill stuff into. And then there's this request pool thing where the request can be part of a pool. So, an example of using it would be something like this. You have your callback arguments where you're basically just counting the number of errors on your completions, and your callback function here takes that request argument and whatever you want to provide to the callback, and then you can pop those arguments off, check the request status, and then increment your error counter in case you saw a completion error, and then you pop the request back or push the request back to that request pool. And then for initializing request pool, here you see the typical queue initialization, and here's a couple of helpers for setting up your request pool and initializing them with the callback arguments and the callback pool. And then the actual I/O path would look something like this, where we're writing a payload to a device. You grab a request, and then you send your write. And in case of submission error, or no error, case 0 here, then you just jump down to next, increment what you were, the pointer to data, and then go back up and submit again and flush your data out. But in case you got errors such as E busy and E again, well, then you have to reap some completions and then try and go back and resubmit. And in case of you get some sort of exceptional error, when you jump out. And either way, once you've submitted all of your I/O and you got an error, well, you end up out here and wait for completion of everything. So this is just an example of how sort of you would use the different, the interface for doing something like flushing a buffer out to your device. So the question is then, so what does this fancy interface cost that wraps everything up for you? Well, it's free as in Apache 2.0. So the cost question is, of course, what is the cost of going through? What is the layer overhead of executing your commands through xNVMe? And I tried to evaluate that using FIO and a 4K random read at QDepth1 to see what was the added latency when submitting submitting and completing an I/O. And I compared that with the sort of the regular implementation of things, so an FIO engine using IOU Ring to an FIO engine using xNVMe with an IOU Ring behind it. And the same as having an FIO engine using SPDK, and then another engine using xNVMe with SPDK beneath. And I did this looking at a physical, locally attached NVMe device, and using a Linux null block instance without the block layer. So this was sort of to see how does this fare on what is available today in terms of your block storage device, and what are the overhead in terms of something where you are not using NVMe but as for your block layer, but actually just want to submit it using any kind of command. So trying here to compare apples to apples, then the latency of these benchmarks result on the physically attached drive, the regular U-Ring was around 8,336 nanoseconds, and xNVMe, going through xNVMe instead, well, that was 8,373. So a layer overhead of around 36 nanoseconds. And doing the same experiment using SPDK again, the latest latency is around this 6,400 and 6,510, which resulted in that overhead of around 39 nanoseconds. So for the physical device, in the ballpark around 40 nanoseconds is what you see when going through xNVMe. And doing the same experiment using a Linux null block instance without the block layer, well, there we have a latency around 644 nanoseconds for not using xNVMe, and with xNVMe, we're at 730, so an overhead of around 86 nanoseconds. So the question is, of course, this is basically the cost of going through the library. I think it's higher here because there must be some latency hidden when actually going through the stack and hitting the drive that we can't see when going through the drive that is exposed when we're just bouncing directly back and forth through the layer. So where is time spent on this stuff? Well, we're doing some function wrapping and pointer indirection. And we're popping those requests back and forth from the pool, and we have that callback invocation. And this is all stuff which the I/O engine does, which the regular IOU Ring engine doesn't do. So there's it's basically just doing more work. And for this part of it, I would say that this is stuff once you have an application, you're quite likely to do this sort of thing anyway. You need a convenient way to call back to your application once stuff is submitted, if you're doing more than just immediately resubmitting without caring about what was actually done. However, there's other stuff in xNVMe right now. Right now it's filling out this IO vec when it does the SQE entries. And I think right now the best way to do this for xNVMe would be use the new feature of IOU Ring, which allows you to just do not the fixed buffers, but just using regular buffers without having the IOV encapsulation. And there's definitely room to improving the request struct and the request layer in the actual implementation. So there's some stuff where I think that's overhead that you'll probably have anyway. Now we just show in the ballpark of what that stuff costs, and then there's room for improving it. So for around 40 to 90 nanoseconds, what else could you buy with that kind of nanosecond? You could do a DRAM load, and it actually costs less than not enabling IOU ring register buffers. So I mention this because our focus is on making stuff easier to use. And if you sit down and have to read all of those specs and man pages, do that for each entry or each interface, you might overlook an optimization. Whereas if you use xNVMe, it'll just enable that for you in case it makes sense. And going through a PCIe switch, well, that's 150 nanoseconds. Going through the block layer, that's around 1800 nanoseconds. And getting a read from today's fast media is around 8,000 nanoseconds. Yeah, and what I want to add to this is just that we'll be working on improving the interface such that the cost will go down. So what do you get when you pay those 90 nanoseconds? Well, you get an easier API. And by easier to quantify that, then the point is that there's less low-level stuff that you need to worry about. You just have, when you want to do a pass-through command, there's one way of describing that, and then the library will take care of mapping that to whatever infrastructure is available to sending that command down to the drive. And there's lower layer stuff like the write barriers and stuff like that. Well, all of that is encapsulated, is really focused on trying to just do a best effort on doing these things such that you don't have to. But if you want to, you can peel off some of those optimize or abstraction layers and then take control yourself. So what you get is that an easy API, and you get that your applications, tools, and libraries will run on Linux FreeBSD and SPDK. And one way of sort of motivating that would be that if all you're going for is performance, you can retarget your application without changing the code. You just point it to a different identifier, and then you'll use that path. If you're in another scenario where you really want the rest of the kernel infrastructure, again, you don't have to change your code, but you can go that way and utilize everything that's available within Linux or within your operating system. And you can do that without changing your code. And there's more. So on top of that base API, there's of course a lot of stuff going on in NVMe with different command sets. For instance, as you heard about today, there are the zone namespaces. So basically building on the base layer, there's then a zone namespace interface on top of that sort of does some of the heavy lifting in getting sending commands in different ways and formulating commands. Also, there's this funky NVMe meta file system that allows you to use file system abstractions to browse through your NVMe drive, where it sort of provides files, binary files of stuff like your log pages on your drive, and also show them in a YAML representation. So you get like this funky way of browsing all of the metadata on your drive as though it was a file system abstraction. And there are some command line tool builders that'll also generate like batch completions for you, and there's some other helper tools. So I guess the last thing is to say that I really hope that I had gotten all of the approvals ready such that this would have been ready today, but I'm expecting to release it very soon in Q1 this year. Yep, so that's it for me. Any questions?
No more questions. Well, I have a question here. I mean, your performance difference numbers look a little bit too good for the bad world we live in right now. Where are your benchmarks with all the fun spectrum mitigations turned off? Because the indirect function calls tend to be horribly expensive with that on.
So this is actually just a regular, it's a Debian installation with a 5.4 kernel. Actually didn't put any, it's not a custom kernel, it's actually just a stock kernel. What I wanted to do was actually try and get a custom kernel running and disabling all of those things. But unfortunately, I don't have those numbers.
Make Linux fast again, work. Beautiful website that gives you the list of all the weird Intel performance mitigations and how you turn. Oh, and actually the kernel helps you too with an all-off now for all the benchmarketeers in the room.
So, oh, there it is. So when I see this, I'm a little bit, why does this make sense? So if I have a normal application, I build my application one way. I have an SPDK application, I need to redesign it such that I kind of submit my IOs like per process and make that optional. So if I want to have an SPDK app, or I want to have a general app, it's two different architectures that I build my application up around. So I don't see that this kind of, if I have to deploy this app and get the benefits, I kind of have to adopt what SPDK does. And if I look at it that way, then what you're saying is we need to go to SPDK and tell them to make a one-on-one, like a better API, such that we can deploy this. So you're saying SPDK's API sucks, and they just need to kind of make it easier. Because if I'm anyway kind of redefining my app, well, wouldn't I just use SPDK, or at least ask Jim Harris in a nice way, couldn't you make it such that I can easily open device? So wouldn't this make more sense to go in and improve SPDK such that they get the API that you're looking for?
No, so, yeah, maybe. So I would say that that's under the assumption that you wouldn't run the same application in the different environments. But I think there is like a class of applications where you're doing basically raw device I/O, where you're sort of throwing away your file system abstractions, all of that stuff. And you do that in Linux. And I would say for that class of applications, this is great. SPDK would do the job. Yeah. Linux would do the job. This sort of just provides a way where you don't have to rewrite that code.
But you're always going to rewrite the app one way or the other. So it's kind of, I mean.
When you're in libaio, you would have to rewrite your application. So, and then you would go down IOU Ring.
Models.
What?
There's two different models. SPDK requires a full rewrite. It's like you optimize with that. libaio, IOU Ring, whatever the Linux model, is two different, you architect your application in two different ways. Yeah.
Let me chime in with you're both wrong.
Awesome. Go ahead, Christoph.
I agree with Simon. I mean, if you have an application that's very low-level centric that you kind of would rewrite for SPDK, in fact, it turns out you need many of the same rewrites to use IOU Ring with all the fancy bells and whistles like the pre-registration. So it would be kind of nice to have one API for both of them, because then you have your app and you say, okay, if you really want to use this with 20 gazillion NVMe drives and you don't do anything else in the box, use SPDK. But if you're actually running this co-hosted with something else, IOU Ring is the way better option. But actually I was saying you're both right, not you're both wrong, sorry. and you're right in the sense of, I think what you're doing would actually be more useful if you contributed that to SPDK instead of adding another wrapper to contribute code to them to make device discovery not suck ass, but actually just work, and by having an IOU Ring backend if you don't actually have a whole device or virtual function VFIO assigned to user space.
Yeah.
I think and Jim
would be happy. We'll make him happy. I like Jim to be happy.
Yeah. Yeah. So I think whether it's its own thing somewhere on a GitHub page or it's part of SPDK, I think both are great. What I'm really concerned about is just making it easier as a programmer and figuring out what it actually costs to have this sort of back and forth and the convenience of doing it. And that's sort of what I wanted to explore here. But yeah, I mean, improvements are also made to SPDK such that NVMe CLI would work with SPDK. They've been trying to do this fancy character device that will intercept your ioctals, and then SPDK will handle them instead of the kernel. So I say that would be a different way of getting stuff to work together. And I say this is another way of getting stuff to work together. Yeah, so that's a lot of ways to doing stuff. But I think maybe, yeah, this would be something for Jim, and let us see.
Your beautiful log browser, I'm pretty sure Keith would love it for his libNVMe.
Yeah. Very cool. Yeah, and I would love to talk more about this offline, how stuff could work together. I mean, when I sit and do an application and try to figure out how to enumerate my drives by running through all sorts of stuff in SysFS, seeing what you did with libNVMe, yes, please. Yeah, so, yeah. I think there's a lot of collaboration to do.